Okay, I think we're going to get started again. Welcome back to the second half of the Art and Pitfalls of fMRI Preprocessing. And I think one little treat is that you have two native English speakers, the first ones. They're coming now. And I'm going to try to be a little more strict with the time, so we maybe have 5 minutes at the end to discuss some general queries. There's already one good query from the audience, which I'd like the speakers to keep in mind. The question was, how does improved time resolution of multi-band imaging either obviate or exacerbate the need for some of these corrections we heard today? So I'm going to try to refer to the question at the end. But now we're going to welcome Rasmus Byrne, and he'll talk about artifact removal and the physiological aspects. Welcome.
All right. I want to start by thanking the organizers for inviting me to give this talk, and also thank all of you for making it out on a wonderful day, and particularly in the morning here. So as I mentioned, I want to talk about removing physiological artifacts. In particular, what I mean by that is removing problems from primarily cardiac and respiratory noise. This is an overview of how I'm going to present it. I'm going to talk about the problems, the issues that we face with each of these fluctuations, but then also talk about solutions to these, and also potential pitfalls perhaps with these solutions, and maybe suggest some improvements to current physiological noise corrections. And then finally finishing up with a couple of just points about things we might want to remember about physiological noise corrections. So in functional MRI, of course what we're measuring is we're not measuring the neural signal directly. Rather, we're measuring the blood flow and blood oxygenation changes that are linked to these changes in neural activity. So sort of the top path, if you will, looking at changes in task-related neural activity causing changes in blood flow, increases in blood, or decreases in the amount of deoxyhemoglobin causes an increase in the signal. And you can get activation maps. I'm also going to in a slide illustrating how we calculate functional connectivity. It could be done from the same data, or you could actually do it from resting state data, where you're looking at similarities in the fluctuations between two regions and inferring functional connectivity that way, based largely on correlations in spontaneous activity, but of course also related to any other mental activity that's going on either during a task or during a rest. And the problem that we're faced with in both task fMRI and resting functional connectivity is that we're influenced by various sources of noise. There could be scanner instabilities and image reconstruction errors, and hopefully those have been taken care of by your MR physicist. But then we have other sources like physiological noise, subject motion, and issues, and that's what I'll get into a little bit more, the physiological noise aspect of it. So in a task activation study, of course what we're looking for is, we have the subject performing some sort of task while we collect a series of images, for example, like this bilateral finger tapping task, and we ask for where does the signal change in this pattern that we had the person do. For example, increases when they're performing task, decreases when they're not performing the task. We can fit a model to that and then indicate those areas with colored regions. In this case, physiological noise will often cause false negatives because it's an additional source of noise on top of this general linear model. The other type of analysis that I bring into now, I know my talk was on functional MRI in general, but I know a lot of techniques more recently have been focused on functional connectivity. And this is actually an area where physiological noise becomes rather important. And the way we can calculate, or one way we can calculate functional connectivity, is by looking at a particular part of the brain that we're interested in, let's say the left region of the motor cortex. And we look at this during rest, and we could ask the same question. You can see the signal kind of increases and decreases, doesn't look like anything particularly interesting. But if we ask the same question, what other parts of the brain have a similar pattern of fluctuation? We end up with this pattern that we see right here, again mapping out all the other areas of the motor system in this particular case. So the idea is that if two parts of the brain fluctuate up and down together in their activity, and they do this during rest, we call them functionally connected. And actually, if you overlap these two time series, you can see that there is some correspondence between them, and actually occurs particularly at the very low temporal frequencies. Now that's one way. There's another way of getting functional connectivity maps out that I have to mention, and that is using independent component analysis. And the idea here is that if we decompose our data, our sort of fMRI time series into a matrix where the rows are the individual images and the columns, if you will, are individual time series. So going down, we have the images going in time. And we decompose that into a series of components in time and components in space. And you can see the graphic representation of that at the bottom. So the idea is that the first area, these all areas colored in yellow would have a particular characteristic time course, and the next areas down have another particular time course, and so on. And so doing this, you could then identify different functionally related networks, areas that have similar fluctuations in time. And you will also see maybe some components that perhaps look more like motion or look more like vasculature. And those could reflect physiological noise. And I'll give some examples of some of the noise corrections that have been developed for that in just a bit. So moving on to the sources of noise, this is where we see cardiac and respiratory noise. The top one shows the cardiac fluctuations. You'll see it's primarily due to the pulsatile movement of the blood. And you can see it very strongly in areas that have pulsatile blood flow, like the circle of Willis and some of these other blood vessels. Breathing actually causes signal changes primarily because of the movement of the chest wall, and that actually changes the magnetic field. And if you map the magnetic field as I showed there on the right, you can actually see changes in it going with the respiratory cycle. And it causes the image to sort of distort or shift in the phase encoding direction, sort of going pulsatile with the breathing cycle. You also see some changes in the CSF. So the other thing to remember, and there's correction methods we have for that I'll get into in a moment, but the other thing to remember is that the brain is not a rigid body. This is some really cool earlier results from Brigitte Poncelet back in the early days of fMRI, and this was actually not even doing fMRI, but just doing senior phase contrast imaging to look at the movement of the brain. And you can see with the pulsatile movement of the heartbeat movement, you actually see a displacement in the lower parts of the brain up to a millimeter or two. So something to keep in mind, that even if we're trying to correct for things post hoc, it may be that you're actually not even imaging the same tissue anymore, and so something we have to be aware of. So the other problem we run into, in addition to the respiratory and cardiac fluctuations that I mentioned, is this one, that variations in breathing can occur or naturally occur during rest, and these can also cause changes in the Bolt signal. So for example, if you were to hold your breath, carbon dioxide builds up, and carbon dioxide is a very potent vasodilator. And so we see as a result of that, blood flow increasing, exactly the same Bolt effect that we see with imaging, and as a result, we see an increase in the MRI signal from holding a breath. Well, these kind of breathing changes occur even naturally during rest. And what you see here is some nice work from Richard Wise from a number of years ago, where he looked at the average gray matter signal and average white matter signal plotted here. And you can see a striking correlation between that and the end-tidal CO2 changes that are plotted there on the bottom. And you can see that it's also spatial heterogeneous, as indicated in that sort of unthresholded map at the top or the thresholded map at the bottom. Now, you can look at this too. I was very interested in it from some of my work. We didn't have measures of end-tidal CO2, but if you just take the respiration trace, and this is an example from a particular subject, and you can see there's periods when they're breathing deeply, periods when they're holding their breath or breathing more shallowly. And if you just look at the envelope of that breathing and you calculate the correlation, this is the map you'd end up with. So striking changes throughout gray matter, but particularly in very similar areas that you saw previously from the work from Richard Wise correlating with the end-tidal CO2. And in fact, if you look at some of my papers that I have on this, if you did not correct for this and you were just able to take a particular time series in the posterior cingulate, which is right in the middle of one of these areas, and did a connectivity analysis, you'd see a map actually very similar to this, suggesting that the connectivity map is very strongly influenced by these fluctuations in breathing, and we really have to take care and correct for this. So there are methods to correct for this. The other method, the other influence, so I'm first sort of listing all the sources of noise and then get into the correction methods. In addition to respiration volume changes, we also have heart rate changes. This is some nice work by Katie Chang showing areas throughout the brain, particularly in gray matter, where increases and decreases in heart rate also correlate with the MRI signal. And it's in fact independent. Here's some example from some of my own work, just calculating heart rate and correlating with the MRI data. And you can see it really does follow some of the vasculature quite a bit, draining vein like you see there. So in order to correct for physiological noise, there's been a large number of algorithms that have been developed. And I apologize for leaving off the author for the last technique, the ICO-Roma. I'll have that citation in a later slide. So I think one of the challenges that, as investigators, we're faced with is trying to figure out, well, with this large range of tools out there, and the list keeps growing each year, which ones should we use? And I can give you some examples of things that I use in my lab, but I would also say that this is really an evolving landscape, and these methods are still being developed. So I'm going to go through some of the more common techniques and just highlight how well these work. So first of all, the simplest you could do is temporal filtering. And the question is, can this really reduce cardiac noise? And my answer to that is not always. And I'll give you an example of this. So here's a cartoon example where you see fluctuations going along at maybe a typical cardiac frequency of about 1.1 hertz. And at the bottom, you see it just sort of plotted in temporal frequencies. And if I were to sample this at a 2-second TR, so collecting a volume every 2 seconds, these are the data points I end up with. And if you connect those dots, you notice it's a much lower frequency. So what's happened is that the high-frequency cardiac fluctuations, by sampling it at a very low rate, has been aliased into the low-frequency band. So if I simply get rid of all of the high-frequency information to say above 0.1 hertz, that's sort of indicated by that dotted line there, I'm still left with all of the cardiac fluctuations in there. So unless you're sampling fast enough, just cutting off the high frequencies doesn't really help. It's not a very good method. Now this sort of brings back the point that was raised earlier. If we were able to collect fast enough, maybe with some of these multi-band acquisitions, then we can use these kind of approaches. And so that's one of the advantages actually of acquiring data much more rapidly so for example, 300 milliseconds for an entire volume is that we can actually start doing more sophisticated filtering methods like just simple filtering to try to get rid of physiological noise. Another method, if you don't have that fast sampling, it's called retro-ICOR. And actually a predecessor to that was from Xiaoping Hu, doing the same thing but in spatial frequency space. The idea here is that you want to measure the phase of the cardiac cycle and the phase of the respiratory cycle that each image was acquired in. And then you construct sines and cosines of those phases and 2 times those phases, or you can do any multiplier of those phases. And you use these as additional nuisance regressors. So another way to visualize this is if I take the time series data, and this is an example from a particular voxel that has very large pulsatile signal from cardiac pulsations. And if I simply reshuffle that data based on the cardiac phase of the cardiac cycle that the data was acquired in, I end up with something that looks like this. And then what we're doing in retro-ICOR is really fitting a lower order sine and cosine to that, variation over phase. And you can imagine if I subtract out that variation, I end up with reducing the fluctuations considerably. And as I mentioned, this was, it's not new. It's been used earlier in actually the very early days of fMRI from Xiaoping Hu, demonstrating that you can get much better task localization and characterization and task activation by doing this physiological noise correction. Now that said, in general, this kind of retro-ICOR or the correction for physiological noise improves your signal by, maybe signal to noise by about 5 to 10%, depending on where you look in the brain. So it's not a huge improvement in terms of how much of the noise you're explaining, but I think it depends on where the regions of interest are. And I think there was some recent paper actually that highlighted the importance of this looking at amygdala because there's some large vessels running right next to the amygdala. So you might want to do some of these physiological noise corrections if you're interested in these structures. So one question is, at what point should this physiological noise correction be done? At what stage? And this is really a bit of a complex question to consider because there's no clear-cut answer. And if you want to hear more about this, actually go into a lot more detail, and a student of mine, Tyler Jones, had a paper on this. And the idea is, well, first of all, you might think that because we're really in retro-ICOR relying on the phase of the cardiac cycle at which each image was acquired, we want to try to do that as soon as possible, basically right after we acquired. Because if you register and move this volume around, you're changing that information. The slices were no longer acquired at a single point in time. But the flip side is that if you don't do the motion correction, what you'll see is that the fluctuation, maybe from cardiac, leaves one voxel and enters another voxel. So you see a decreasing in amplitude, and in the neighboring voxel, if the person is moving their head, you see that fluctuation increasing. So again, those time courses are not well modeled by the motion regressors or the physiological noise regressors. So ideally, we could come up with a combined approach, and in this paper, we actually described theoretically how that would work. Interestingly enough, in practice, it didn't seem to make much of a difference. But by looking at various orders of this, we found that actually doing the motion correction first and then the physiological noise correction tended to give us a bit better results in terms of better signal-to-noise ratio. And I think the reason for that is that motion in any 3 dimensions would cause the fluctuations to move from one voxel into the neighboring ones, but only motion in the through-plane direction is going to disrupt the timing information. And in this case, if you're collecting sagittal slices, as we were doing, most of the head movement tends to be a head nodding movement, and so it's predominantly in slice, and it's not going to destroy the through slice information as much. But I think there's some further work that could still be done in really trying to merge all of these tools together, for example, particularly with slice timing correction, and how to work that in. In order to correct for the respiration volume and heart rate changes, one technique that's been proposed is RVHR core from Katie Chang. And in this example here, you can see, this is now on 3 subjects, that combining the respiration volume and heart rate together, you can account for significantly more variance than either of those alone. And the idea is then you create those regressors, you remove that from the data. That's one way, just as a zoomed in if you want to see that. Now, another approach, and this is the one that I'm using predominantly in my lab, is to derive the nuisance regressors from the data itself. And the idea here is that we perhaps want to average regions of the signal that we expect not to contain a lot of neural activity. For example, the white matter or the CSF, and particularly the large ventricles. We generally don't expect neural activity, and particularly the bold effect, to occur in these areas very strongly. Yet we do see physiological fluctuations in them. As I showed from Richard Wise's work, where he averaged the signal over the white matter, you do still see a correspondence of that with the end-tidal CO2. So regressing out the white matter and the ventricle is one additional way to try to remove physiological noise. Another thing that people have proposed to do is looking at the global signal. Let me see if I have, yes. And the reason for that, so this is basically averaging the signal over the whole brain and then removing and regressing that data. The argument being that if things change globally over the whole brain, as we see breathing changes also occur globally throughout the whole brain, we're less interested in those. And in fact, if you calculate the correlation between the respiration volume per time, the RVT changes, and the global signal, you see that in most subjects you have a pretty strong correlation between the two, sort of around 0.5 on average. And if you were to calculate functional connectivity maps, say from a posterior cingulate region to look at the default mode network, at the top, this is the map you'd end up with, and you can see pretty strong correlation throughout the brain. But you do see hotspots in areas of the default mode network. And then the bottom is what you get with global signal regression. And the hotspots are much better localized after you do the global signal regression. So that's one advantage why people like to do it. The problem with it is that by definition, the global signal includes the signals that you're interested in as well. And it can be shown mathematically that you can introduce anti-correlations when you've done this global signal regression step. So on the bottom is what you see, a connectivity map when you don't do global signal regression, and at the top is what you see when you do global signal regression. And you see these anti-correlations. Now, there was some work previously to that from Jonathan Power and others, suggesting that we have this interplay, this anti-correlation between task positive and task negative regions, and it certainly makes a lot of sense that as you ramp up activity in the default mode network areas, these are the areas that are more active at rest, as you decrease the activity in those areas, when you start performing some sort of task, you have this sort of negative relationship between task areas and this default mode network areas. And actually there has been some subsequent work to this showing that even in the absence of global signal regression, you do see this anti-correlation, and even in animal models, you start seeing this anti-correlation. So I do believe that this negative relationship between default mode activity at rest and the activity in the task positive areas is probably real. The problem is we know that it's possible that this kind of preprocessing can introduce false connections. false negatives, as you see here. But even more problematic, this is some work from Ziad Saad, just in a cartoon example, showing that these kind of corrections can also influence or can also create group differences where there weren't any before. So what you see there on the lower left, or on the panels on the left, is an example of two groups. And the only difference between the groups in this simulated toy example is an increase in the long-range connectivity. Now, when you do this before any global signal regression, you can see clearly that's where you see the change. If you do global signal regression and then look at the difference, you'll find, of course, that big change in the long-range connection, but you'll also see a decrease in the opposite direction in the local connectivity. So you've actually introduced group differences where there really weren't any to begin with. And there were some follow-up studies to this by Jonathan Power and the group in WashU looking at this more carefully. And I think there's still some disagreement in the field of how prominent this really is. And part of the issue there comes in how close to reality these kind of toy models is. The arguments of, is there enough balance between all the networks that the activity, the fluctuations in any one network is not going to outweigh and start skewing these. But I think this is a big enough problem to be aware of that currently in my lab we're not using any global signal regression. Rather, we're looking at alternative methods to correct the data that don't run into these potential problems. So what we basically do is we just use the white matter and the CSF, the eroded ventricle signals. Another technique that's been proposed is called PST-core, or phase-shifted soft tissue correction, from Jeff Anderson and colleagues in Utah. And the idea there is, in addition to white matter and CSF, you also bring in signals which are averaged from the edges of the brain, right, particularly in the soft tissues in the face. And then the additional step they do is they also shift the white matter and CSF signals and the soft tissue signals to have a maximum correlation on average across the brain with the gray matter. So to account for differences in latency between the white matter signal and the gray matter signal. So this is what I was just alluding to in sort of my response to the last question. Here's what you get when you just take the connectivity maps from each of these different correction methods and all threshold at exactly the same individual voxel threshold. And it's clear you can see that the biggest effect by far is by removing average white matter and CSF, or by the global signal, and you can even see the introduction of these anti-correlations in the global signal. Now, if I change the threshold on those first four maps just to see, can I make the areas look similar? Sure. We can actually get very similar looking maps just by increasing the threshold and that. They're not exactly the same. And so the other thing we can do is we can actually do a t-test and see, okay, what are the significant differences relative to no correction? And you can see that retro-I-core accounts, this is not the additional variance explained. This is the difference in the connectivity maps and looking at the t-test and how the connectivity map has actually changed. So even though within the first three that you see here, retro-I-core, RVT-core, RVHR-core, it doesn't look like they're different. When you actually look at the t-test, there are areas of significant difference showing up there. So even though it doesn't look like it on our actual maps in terms of the overall group map, when you actually look at the statistics, you find that there is a significant improvement or a significant change in the functional connectivity of the posterior cingulate. And then, of course, huge changes with white matter, CSF, and global. These are the areas that show the biggest signal change. This is now just looking at the R squared relative to no correction. And the interesting thing here that I want to point out is that the first three, retro-I-core, RVT, is basically using the physiological signals. And I should point out RVT-core incorporates retro-I-core, and the same with RVHR-core. You see a lot of variance accounted for in the circle of Willis in these pulsatile areas. Whereas when you do the white matter and CSF and global corrections, you account for a lot more variance, but in particular in these draining veins, but not at all in the circle of Willis. So just by doing white matter and CSF and global signal regression, you're not accounting for that pulsatile blood flow in the circle of Willis. So there is some value to having the actual physiological signals in addition to the global and white matter and CSF. Just as a couple, because I know I'm running short on time, but where can we go from these improvements on this? One is very similar to the PST-core method, is allowing for a shift in the latency. We can show, as I've shown in some of my earlier studies, that the optimal fit of this respiration response function actually varies across the brain. And if we allow that to vary, we can account for significantly more variance. And similarly, if we allow for variations in that response across different subjects, we can account for much more variance. So this is a study from Mariam Falapour, working with Jerzy Badurka, and they're showing that if you look at an individual RVHR core, again, that accounts for significantly more variance. So deriving the respiration and cardiac response function on an individual subject accounts for significantly more variance. Just as a couple of final other strategies out there, one is the fMRI-B's ICA-based X-noisifier. One of my favorite acronyms, just FIX to get rid of it. The idea here is to use ICA and decompose the signal into spatially independent components and then look for what components might be artifact versus true signal and reject artifacts that way. This particular implementation initially had a machine learning algorithm, and the user had to train this algorithm initially, but there's been some advances on that. This is actually now in the context of motion artifacts, this ICA aroma technique, to automate this process of selecting what components might be noise and what components might be true signal. And I can imagine perhaps something similar for physiology. Let's skip over that in the interest of time. So finally, just wanted to leave with the thought of, should we perform the physiological noise corrections? First of all, I have shown here, and there's others have shown, that this does reduce fluctuations related to heartbeat and related to respiration variations, reduces false positives, reduces false negatives. Probably less of an effect on regular task fMRI unless you're in areas that tend to be close to pulsatile vessels. Finally, the thing to remember is that sometimes the physiological fluctuations might be associated with variations in neural activity. For example, heart rate variability. I talked here about the potential sources of noise that heart rate can cause, and you can see that they map throughout gray matter. But my psychiatry and psychology colleagues often use heart rate variability as a measure of interest about the person's behavior. We actually have seen some of these examples ourselves, that in some cases, in some of the tasks that we were doing, we actually saw correlations between heart rate changes and the particular task they're performing, and so it's something to be cautious of. We might not necessarily want to remove those fluctuations. So with that, just wanted to, hopefully I've given you an overview of the different ways of correcting for physiological noise and the various influences they have, and thank you for your attention.
We've got time for some quick questions, or one quick question.
I actually have a question, if you don't mind. So when we're regressing out the CSF signal, I have seen many times that when we analyze the task-based data, there's a deactivated area inside the CSF. So even though there's no neuronal activity there, but there are blood inside the CSF, and that shows up to be negatively related to your task. So if you regress out those signals, what do you think we will remove some of the effects that we're interested in?
Yeah, so I mean, if you have CSF signal that's negatively correlated with the task of interest, then because the regression doesn't care if it's negative or positive, you would remove that component, potentially remove task of interest. So it is something to be aware of, and maybe, I mean, the nice thing about task activation is that you can start testing for these effects. With resting state, it's a bit harder because we don't know what the timing is supposed to be. But perhaps a good lesson for this would be actually to calculate the correlation between the task and whatever nuisance covariates that you want to include. And this goes not just for physiological noise, but also for motion regressors, for example. If your motion is correlated with your task, removing it could cause problems.
Okay, one last, and then we got to move on.
Thank you for the excellent talk. I just have a very, I'd just like to hear your opinion on externally measured physiological monitoring device, such as a prospective motion correction system that actually can measure the movement parameters, for example, or the biopack system that typically you're able to measure the physiological, like heart rate and breathing, these independent systems that are able to sample at a much higher rate than fMRI systems. So, like, do they actually bring a positive impact to the pre-processing steps?
Yeah, so I mean, I focus mostly here on the physiological monitoring. In terms of the prospect of motion correction, that's really interest of mine as well, perhaps more related to the motion. And there's some great external tracking systems. The one thing to worry about is, if you put a marker on someone's head, is their forehead going to move relative to their brain? But in terms of the physiological noise, there is certainly an advantage for externally measured traces like I showed here with the retro core, the kind of techniques you can do that is hard to do when you don't have measures of that. I would say that there's quite a bit of variation among manufacturers out there in terms of the quality of the respiration measure with the respiration belt, and so that's something to check. A lot of them just use like a BioPack system. It's highly nonlinear in its relation to the respiration depth. So that's something to be aware of. It still works to the large extent, but if you have something that's a bit more linear, that's perhaps pneumatic based, it tends to work a bit better. So.
Thank you.